Alright, so welcome to video series 4. Even though we're in week 2, we're going to start video series 4. One way ANOVA. We're going to go ahead and start with the research question. Are the likes on posts similar across 4 Cal Poly related Instagram accounts? So this is me going out there and using real data outside of the stickers. But in this situation, I go through the thought process of actually finding the accounts, which accounts do I want to follow, or at least analyze, and then discussing the design regarding me getting this data. So real fast, okay, we're trying to figure out, how do people interact with Cal Poly associated accounts, okay? And so what I did was I looked at any account that had more than 7,500 followers, and I just randomly selected 4 of them. And then what I did was I visualized, at least I investigated 20 posts from each account on April 28th. The reason why I needed to mention this date, because you know that it could change. People can go back and not like it, which I doubt, but people can also like it even more, okay? I collected the URL as the ID. Doesn't matter whether or not it was a video, the number of images, and so on and so forth, okay? A bunch of quantitative variables. The posts were selected 4 to 5 months prior. So I found posts that were 4 to 5 months that people post essentially in November 2023. And the reason why I would do that is because I would say that those posts are pretty much in cement. There are some people that go back and like images, but most likely it's pretty much fixed, almost there. Those images or videos. The selection processing involving 20 posts in a row from each account. How could this be problematic? The reason why this is problematic is because individuals that post, it's seasonal. So it could be in football season, so therefore all the football people are watching football, so therefore those 20 in a row are going to automatically be very similar to one another. This is not really a random sample, because we did 20 in a row. The reason why I did 20 in a row, because I don't have time to just scroll on Instagram. Okay. In this context, the population could be considered all Cal Poly related posts on Instagram, and the sample could be 80 posts selected from November 2023. Okay. But at the same time, that's just one way of looking at the population. Okay. This raises the question, an important question: how representative is the sample of the overall population? And there are a lot of and other limitations or biases in the sampling method that could affect the results. I would say yes. It's not representative because, mind you, we're looking at a particular season in which we're actually getting this data in April from November, in which students, let's say for example, are in final exam week, or not final exam week, but midterms. Alumni might not necessarily look at it, at the post in that regard at that particular time of the year. There's a lot of different biases that can come up when it comes to actually drawing this sample. All these some things that you should be aware of. All right. So with that being said, let's go ahead and jump into the SSVA of this data set. So the summary statistic. Before I even do that, my apologies, let me take one step back. I don't know, is it clear what the explanatory and the response variable are from this question? Okay. The explanatory variable, or at least one of the variables is going to be the Instagram account, and then the response variable is going to be the likes. The reason why I needed to stop and go back there, because when it comes to making this summary statistic, or creating the summary statistics, I have the mean and standard deviation and the sample size for what? So the mean is the number of likes, standard deviation the number of likes, and then we have the 4 different Instagram accounts. As I said, I collected 20 from each of the samples, from each of the posts, each of the accounts. So therefore, that's why we have 20 for each one. That Cal Poly one is, doing really well, but at the same time has a lot of variability. Okay. This is my visualization. This is what I call a violin plot. This is very similar to a box plot. Okay. In that it shows the distribution of data, but this one actually shows you the density. It shows you that most of the values are closer to the middle. These is closer to the bottom. This is closer to the middle. This is closer to the bottom. where the density of the data is. That's why I like to use this particular visualization. What do you think the white dot represents? If you said the mean, good job. The white point represents the mean of the likes. Okay, and the height of each of the bars represent the variability in our sample. Okay, which is nice to see. All right. So with that being said, the analysis looks like this. Okay, the biggest thing to note is the corresponding p-value right here. Okay, the p-value is 2.2 or 2 times 10 to the negative 16. That's very, very small. And this is our corresponding test statistic. Okay. When it comes to one-way ANOVA, I'm going to talk about this in a little bit, but this is the post hoc method. The post hoc method. And the post hoc method actually does a bunch of, or let's say to be exact, 4 times 3 divided by 2 comparisons. So the reason why I say 4 is because there's 4 groups. Okay, times 3 is the equation, divided by 2 tells us the number of paired associations there are. So 4 times 3 is 12, divided by 2 is 6. So there's 6 different comparisons. So what this is doing is looking at Cal Poly versus Cal Poly ASI, Cal Poly baseball, Cal Poly football, Cal Poly ASI with Cal Poly baseball, Cal Poly ASI with Cal Poly football. You can't get the point. And then these are all the comparisons. So with one-way ANOVA, the primary purpose is to see if all the population means are the same. Population means are the likes. Whereas for Tukey's HSD, once we reject the null hypothesis, we need to figure out which of the pairs are different from the others. Which of the pairs are different from the others. If we decide to fail to reject the null hypothesis for one-way ANOVA, we would not do a post hoc method. We would not do one. All right. So continuing on, okay. These are the assumptions for one-way ANOVA. One of the first assumptions, independents are random assignment. In this situation, our groups are, there's a common theme, but one can argue that they are independent. This is not an experiment, so it's not random assignment. So this is going to be a somewhat independent group because the people that run each of the counts are independent from one another. Equal variance means that the ratio of S max over S min is less than 2. Or the standard deviations, the variability is about the same for each of the groups. You can see in this visualization that assumption is not being met. Okay, so take a note of that. And if it's not, you just note it and keep on going. Normality of the response variable. Normality of the response variable, we're assuming that most of our data, or at least our data, follows a normal distribution for each of the response variables. And this is how we visualize this using a QQ plot. We want most of our response variable, whether it's, for all 4 of the levels, we want them to be normal. And the way we visualize this is by using the QQ plot. So we would want all the points, or most of the points, to be close to this red line. Okay? And that's how we visualize it. Last assumption is that the data is random. The last assumption is that the data is random. Okay, the data is random. And so what does that really even mean? What first way of thinking about it is that the data is randomly selected for each of the groups or each of the posts, or we randomly assign individuals to a particular treatment. Right now, this is not an experiment, but if it were to be, if we were to randomly assign individuals to an experiment, that random assumption, or at least that level of randomness, would be accounted for. That assumption would have been met in that mechanism. With that being said, let's move on to some questions. So ideally, you would have solved them before just looking at me solve them. So simply going back to question 1, we know what it is. What is the population of interest? Okay, the sample, say the observational unit. The population of interest is going to be the 4 Cal Poly Instagram accounts posts that denotes the 4 populations. Okay, so technically one could argue that there are 4 separate populations, but one can also argue that's going to be all posts from the Kyle Poly Instagram account. So we're gonna go with I'm gonna go with there's technically 4 separate different populations regarding the Instagram accounts. The sample of interest is going to be the 80 posts, right? There's 20 from each of the Instagram accounts. An observational unit is going to be a post. Okay, a Kyle Poly related post on Instagram from one of those 4 accounts. Okay. With that being said, number 2, state the variables. There are 2 variables. Okay. One is going to be the Instagram account, and the second variable is going to be the number of likes. Okay. What's the response variable? The response variable is going to be the number of likes, and then the explanatory variable is going to be the Instagram account. The Instagram account is going to be categorical, and the number of likes is quantitative. And the Instagram account has 4 categories. What other variables did I collect? Also, what else did I collect? I forgot already. What should I also collect? Let's see what the answers are. So I collected whether it's photo or video, number of images on the slide, number of comments. I could have collected how many days since it was last posted. So yes, it was 20 days in a row, but it doesn't mean that 20 posts in a row. It doesn't mean they all posted on the same exact days. So that's a variable of noting. Okay. Tell me your thoughts, other variables in the comments. All right. That'd be kind of cool, I guess. What is the parameter of interest for each account? Technically, it's going to be the population mean, mu. Describe it what the parameter is. It's going to be the population mean of likes from that Instagram account. Okay. And so that is what we see here. All right. So state the non-alternative hypothesis. And you know what? I don't say this here, but maybe I will say this in the question. Also, state the statistical technique. State the statistical technique used in this question. Okay. So stating the null hypothesis. The null hypothesis is that all the population means are the same, and the alternative is that at least one of the population means are different. Please note that at least one is different. So we're going to assume that they're all the same or they're equal. Okay. So it's not the same value, but they're just the same. Okay. And then at least one of the population means are different. So this is in symbols. I mean, this is in words, right? And these are some key indicators. You have to have the population parameter. If you do not, points will be taken away. And then these are in symbols, and there's no way to symbolically describe what it is, what the alternative hypothesis would be. So when it says state the statistical technique, I'm going to say one way. This is what we call one-way ANOVA. And the primary purpose of one-way ANOVA is to determine if the population means are the same across multiple levels. This is more than 2. We could use it for 2, but that's again bringing a gun to a knife fight. So that's that. So when it comes to how do I describe the center and spread using the sample statistics of each account's number of likes, center is the mean or median, and spread is the amount of variability. So how the actual height of each of those violin plots. So here we go. Spread numerically, I said using description. So the mean is the center, and then the spread is the standard deviation. My apologies for that. And then from there, here are the actual values, the actual statistics. Okay. So there's a reason why I do this. I mentioned this because you're going to see this in a little bit. So here, state the test statistic. Okay, this is the test statistic. Sorry, this is the F distribution for our test statistic. And if you go up, you can actually find the test statistic in the R output, and that's important information to note. That's 58 54.81. So you look at the graph, 54 is not even here. So 54, if you were to draw that vertical line will be like far away. Oh, wow. And then the area underneath the curve, the p-value, would be even very, very small. So with that being said, let me write this. Ugh. Okay, so the test, I think I already wrote it down there. I did. No, I didn't. Oh, wow. So the test statistic is going to be, like I mentioned earlier, 54, and the p-value is, so let me just make sure I have that. So this is the test statistic, and this is the p-value. So the p-value is actually less than 2.2 times 10 to the negative 16. This video is getting quite long. I think I'm gonna have to do a part 2. Okay, so let's do that. Pause it, we're done. Thank you.